So we looked at the dot product yesterday. Let's now look at some applications of the dot product. The angle between two vectors. We saw that in 2 dimensions. Again, because we're using vectors, the formula in itself is dimensionless, because it could be a 2-dimensional vector, a 3-dimensional vector. It doesn't change. So if I now have to find the angle between these two vectors, alright, so the dot product on the top, so -4, +4 and 3, and then the two magnitudes on the bottom, we end up with 3 on 7 root 6, and it works out to be around 80 degrees to the nearest degree. Then you'll recall this idea of vector projections, where we project one vector onto another, and this was our formula that we ended up with. So it was u dot v over v dot v times the actual vector it's being projected onto itself. Make sure you read the question. Notice this says find the length of the projection, not the projection itself. So that changes the formula slightly if I just want the length of the projection. So it becomes u dot v, that stays the same on the top, but the bottom becomes the magnitude of v. So subbing into that one, and we get 5 on 3. But let's do one where we're actually finding the projection. So we're going to project u onto v. So u dot v on v dot v times v, subbing all that in, and there it is. Whether you leave it factorised or whether you expand it out, I suppose it doesn't really matter. I mean, it's still the same thing either way. I tend to like to expand something like that out though, so you sort of got the 3 separate components. So let's go back to this idea of perpendicular distance. And we have a perpendicular distance formula for 2 dimensions. That's the point to the line. What we saw in our daily quiz yesterday was that formula projects through, but that's not for a point to a line. That became from a point to a plane. So how do we do it in other dimensions? This is the situation we're basically talking about. If I want to find the perpendicular distance from a point to a line, the line I've called mn. But if I think of it as vectors, I could say I want the projection MP, then that'll create one side of a right angled triangle. I can find the length of that projection, and then the third side of the right angled triangle would be the perpendicular distance. Essentially, that's what we would do. So MQ, that vector, will be the projection of P onto N. MQ, MP plus PQ, if we did addition of vectors, I can rearrange that. Remember, it's PQ, it's the length of PQ I want. And we end up with MQ minus MP, which is the projection of P onto N minus P itself. So thus our distance would be the magnitude of whatever that vector ends up being. Alright, well let's try one. We're going to find the perpendicular distance from A joining B and C, and they're the coordinates that have been given to us. So P will be BA. Now I didn't draw up a diagram here, but possibly a diagram would be handy to get a feel for which one's going on to which. And then I can work out BA, head minus tail. U I've called BC, so that's the vector I'm going to project onto, and that becomes I minus J. We've said our distance will be the magnitude of that projection minus the vector P itself. Now I've done all the working out in one hit here, but the projection of P on U would end up being this, because I minus J, that is U, and if you work out that U dot V on V dot V turns out to be a half. And then we're going to take away our vector P, but we want the magnitude of that, and that all works. Again, I've done all the calculation in one hit there, but ends up being root 22 on 2. So that's how we could find the perpendicular distance of a point to a line in any dimension. We're going to classify the triangle formed by joining these 3 points. What sort of triangle do we get? Well, let's see what the sides of this triangle are. So AB, the vector AB, there it is, 3, 2, 1, BC, and CA. Now, how can I classify it? How do we classify triangles? Well, it's either by their sides or their angles. So, and we have, scalene, we have acute angled triangles, we have right angled triangles, and of course we could have an obtuse angled triangle. Oh, and then of course you can have isosceles, and equilaterals. That's to do with the sides, of course. So I think I went with the sides first because they're probably the easiest things to find, is the length of the sides. And let's see what's happening. So the length of AB is root 14, the length of BC is root 12, length of CA is root 2. And I notice, hang on a sec, this is going to satisfy Pythagoras' theorem if I play around with these numbers. Because CA squared plus BC squared will be AB squared. ABC is a right-angled triangle. Of course, I could have played around with it and gambled, and now at this stage I can gamble because I know the answer, and I could have played with the dot product and magically gone, oh, I wonder what the dot product of BC and CA is. Now, if I happen to have gambled and picked that, that's going to be quicker, but gee, I got lucky if I happened to. But all right, if I had got lucky, then we go, oh, look, they are perpendicular, well, therefore we've got a right angled triangle. ABCD is the base of a square pyramid. A pyramid's got sides 2 units. That's the base, that is. V is the vertex. It's symmetrical. Height's 4 units. We want to find the angle between one of the slant edges and the base of the pyramid. Now, we did these sort of questions last year using 3-dimensional trig ideas, okay? Which is a fair enough way of solving this problem. If they were to force my hand, and I haven't in this question, but if they were to force my hand and say, using vector methods, then I've got to tie vectors into this. I can't just go and use the trig and go bang. So let's assume that's our problem. Therefore, I'm going to sit it on our Cartesian space. Now, because it's symmetric, it makes sense to sit it right in the centre so that the vertex is on the z-axis here. I can now create some coordinates and some vectors. See, if I want to find the angle between one of the slant edges, so the slant edge I've done here in blue, this point here would be 110 because they told me the base was 2 units. And I know up the top here that must be 004 because they told me the height was 4 units. I guess that's the advantage of placing it symmetrically though, because you get a whole heap of zeros in your coordinates there by sitting it on the centre. Let's work out what that vector is. So -1, -1, 4 would be that vector. There's the other vector I'm going to need to find the angle between the slant edge and the base. You've got to imagine, I guess, slicing the pyramid down there to get a nice 2D shape. It'll allow you to find it. And that vector is -1, -1, 0, not 1, 1, 0. Remember, head minus tail. The tail is always the point of intersection of your lines. Okay. We know cos theta then would be u dot v over the magnitude of u, magnitude of v. So subbing into that, we get cos theta is 1/3, 71 degrees. Actually a lot quicker than doing it using our 3D trig ideas. Because using 3D trig, I would have had to pull out all these different right angles, find lengths of sides, and bang, this sort of does it all in one hit. The medians of a triangle meet at a point. Okay, we know that. Prove that the medians divide each other in the ratio 2:1. 2 dimensions, 3 dimensions, I suppose it doesn't really matter, because at the end of the day with a question like this, it's dimensionless anyway. Because we're just talking about something that's going to sit on a plane. Now that plane could be in 3 dimensions, it could be in 2 dimensions. They haven't given us any coordinates, so it's really exactly the same as something we would have seen in extension 1. Alright, I'll call OAB our triangle. O gives me the reference point, it's convenient to get my head around, oh, I'm going to make that the origin. I'll just call that vector A, I'll call that vector B. So the midpoint of OA I'm calling X, and the midpoint of OB I'm calling Y. Now we want to prove that the median is the line that joins the vertex to the midpoint of the opposite side. So let's draw those in. They meet at a point, I've called that point Z. Okay, I want to show that they're in the ratio 2:1. Well, I'm going to draw in the third one. The position vector for Z is going to be handy. So let's call that Z. Now, Z is going to divide in some ratio. I'm going to call it M to N. So I know that the ratio of A to Z to Z to Y, those vectors there, is M to N. So therefore, playing around with it, I get that N lots of AZ is M lots of ZY. I'll substitute in head minus tail, but of course Y I know is half of OB, so it's a half of the vector B, so I've substituted that in. Z is what we're what we're playing with, we want to find that. So n plus nz is equal to na plus mb on 2. Let's keep playing with that. Similarly, z will also divide ay in the ratio m to n. It's going to be the same ratio, we just want to know what the ratio is. So m plus nz is equal to nb plus ma on 2. Playing around with that one, and we end up with that expression there, but that comes back to, there it is, that's what we got in the last one. So substituting in, we get m over 2 is equal to n, so there's our ratio. m over n is 2 over 1. So okay, so we know our medians divide each other in the ratio 2 to 1. So we looked at the dot product yesterday. Let's now look at some applications of the dot product.